average of all the columns. Okay, and then I do the search within the what is that? The projection, the row projection and the column projection. And based on the triangle inequality, I know that if you're not matching well in this space, then forget it. You can never be a good candidate. Okay? If you're not a good match in the projection space, okay, you get eliminated. Okay? And then you only have a few guys that you really have to check. The guys that actually pass all the row projection and column projection tests. Okay? So that is another algorithms that seems to be working really well when exhaustive full search is concerned. We want to really check everything and do not want to miss it. Okay? So this can be combined with spiral search and early termination like the one that we had before. Okay? This strategy can be combined with the spiral search and the early termination you had before. Whenever we cross that bar that we found, you get eliminated from the search. Okay? Now, so let's spend. Okay, yeah, that's right. Another type of smart motion estimation is called spatial correlations. And this is based on the observation that typically neighboring blocks move together or stay together. They either move, right? You have a block, an object, which consists of many small blocks. Object moves mean all the blocks kind of moves together, or all the blocks belong to the background and they stay together. Okay? So if you already do motion estimation for 1, 2, 3, 4, correct? When you get to this guy, you already process 1, 2, 3, 4, correct? Okay? So then you have the information on the motion vector of 1, motion vector of 2, motion vector of 3, motion vector of 4. You base on that, you predict the motion vectors for C. Right? It's a smart strategy. And then you should check that prediction first. Get a very low bar. Then after that, you apply early termination. Right? So that is a very, also another smart motion estimation strategy that will lead to optimal motion judgment. Yet faster, right? So let me give you a few examples. This is a previous frame of the Glasgow sequence that we play around with. Okay, I don't know what frame, maybe this is frame 24 and this is frame 25. Okay? This is the current frame that I have so far. And these turns out to be my motion vectors. You see all the red little things? Okay? The red little guys right here, they are the motion vectors. Okay? And if you come close, I'm telling you right now, they're pointing this way. They're all pointing this way. I think this is part of your math lab exercise today. Is that true? All the motion vectors, as you can see, is pointing the same way, okay? Which indicates that this is a panning type of motion. Okay, somebody is taking a camera and doing this type of panning. So it's not the dome is not moving, the camera is moving. That's why. Okay, so this is a very typical behavior of a panning sequence. Now, if you take a look at, so if you just simply take the frame difference, this is what you get. Take this, subtract that, display the absolute value, this is what you get. Take this, subtract that, taking into account the motion vectors. Motion estimations is really powerful in video coding because you generate, see, instead of encoding this image, right? If you do not do any motion estimation, you have to encode this image, you have to encode that image, right? Instead of encoding this image, you can just do encoding this image. So it's a lot easier. Okay, another example. Maybe this shows up a little better. Okay, you see all the red arrows? Those are the motion vectors. Okay, so at first glance, you see that these two frames look exactly the same. Right? Mother holding her daughter, and doesn't seem like anything is different between these two. But if you take the difference between the two images, you come up with something like this. So it indicates that the woman is moving her head. The background stays. See, the pictures here stay, the picture here stays, so you don't have any motions in this background. The child seems to stay. She is staying pretty still, but the mother is moving. Okay? The mother is moving. That's illustrate local motion. Okay? Usually motion is very local. So if you take the frame difference, this is what you get. Okay? If you do motion estimations, this is what you get. And the fact that you don't have any motion vectors up here means what? Background stay perfectly still, you get 0, 0 motion vectors. Agree? You get 0, 0 motion vectors. So when I plot 0, 0, it doesn't show up here. Okay? It only show up, so for example, these guys might be 1, 0 or 1, 1. Okay, that type of thing. Now what happened to this arrow? And what happened to this arrow? What happened to these arrows? They're moving far away. Okay? Now this, I want you to observe another thing. Motion estimation, the way that we are doing it, is not perfect. Okay? It's not always match the exact motion of the object. It's an ad hoc procedure. We do not take into account the object. We only care about the best matching plot, no matter where it is. Okay? It can be really, really far away. I don't really care. Okay? As long as it gives me very, very small errors, and I'm happy, right? So in a lot of cases, especially when you have blocks near the boundary, a lot of strange things happen. Okay? It just happens that this gives you the best match, and that's it. Okay? So, should we take a break? Let me check out what I have. Okay, this is in the past, this is in the future. Okay, how can we observe the future? We just delay. We just delay the operations. Okay, we delay the motion estimations. We capture the future frame first, and then we start the motion estimation process. Okay, so you can search over here in the past. You can also search in the future. And that turns out to be a technique we call bidirectional motion estimation. So B hat, which is the estimation of this block, can be a linear combination of C1 and C2. Okay? So it can be forward only. For example, A2 is 0. A2, alpha 2, right? Alpha 2 is 0, meaning you only search in the past. Okay? Or the best match happens to come in the past. And then it can be alpha 1 equal to 0, means the best match only comes from the future. Okay? Or it can be a combination of both for whatever reason. Okay? So in this case, you always get much better motion estimation. At what cost? Double the computation time and delay and very good. And agree? So that's where it will get you. Okay, and this is a demonstration of how sometimes using both backward and forward give you a better motion estimation. Okay? Now you can generalize this scheme even further. You can say, wait a minute, I'm going to do multiple reference frames. Right? So I use frame -1, use frame -2, and also use frame -3. Okay? To find the best match. I don't have to always have to use this same frame.